Okay, for section 7.5, we are finally going to talk about the unit circle. So the unit circle is a way for us to remember some commonly used angles and the trig functions surrounding those angles, okay? So we have a little bit of work to do to build up to that idea. What we're going to do in this first video is technically review, but we'll take it nice and slow to make sure you're good. So hopefully you remember that back in 7.4, we were talking about finding trig functions of any angle, okay? Any angle at all. And we drew a picture that looked like this. We're like, okay, we have our Cartesian plane. We're going to draw an angle in standard position, so the vertex at the origin and the initial side on the positive x-axis. And then for the example that we had, we swept open in the counterclockwise direction and we drew an angle like this. Okay, now we had some information on this angle that was really, really important. We said, hey, imagine a point on the terminal side called AB. And then that distance from the origin to the point on the terminal side, we called it R. And we use this to basically define the six trigonometric functions. And it took us a little while in that worksheet, but we finally got to this idea of a reference angle. So we had these reference angles. So a reference angle is basically the angle that is created from the terminal side of some other angle theta and the x-axis. So we're like, okay, so imagine we have a little reference angle here. We could call it alpha. And then using that, we know that when you're dealing with the six trigonometric functions of theta, they equal plus or minus the six trigonometric functions of alpha. You just have to be careful of what quadrant your terminal angle is in. So we had this idea of this reference angle, and it basically allowed us to build a right triangle where we had a distance A and a distance B, and we were able to say that sine was B over R, cosine was A over R, tangent was B over A, cosecant was R over B, secant was R over A, and finally cotangent was A over B. Okay, well, we're just reviewing that here. Okay, we want to review that same exact idea here, but let's go ahead and just acknowledge that that point AB lives in the Cartesian plane. It is a regular or old order pair, so let's just go ahead and call it XY. Okay, why not? Let's call it what it is. Okay, so for topic one, we're going to talk about properties of trigonometric functions, and we're basically going to review what I just told you. Okay, so it says given the angle theta and a point on the terminal side, we're going to call that point xy now. Okay, now before we called it AB because we had like the adjacent side and the opposite side, and we're used to drawing right triangles with sides A, B, and C. Now we're just going to admit we're in the Cartesian plane, it's xy. Okay, so we have a point xy on the terminal side that is a distance r away from the origin. The six trigonometric functions are defined to be the following. Okay, so we have this image here. Let's go ahead and draw our angle. So standard position, we have the origin where the vertex is, the initial side is on the positive x-axis, and we sweep open in the counterclockwise direction, and we have our terminal side, and we're like, ooh, look, we have this point xy on the terminal side. Well, what we can do with this is we can essentially create a right triangle. Okay, you can see I've kind of got it here. We've got basically a right triangle. The base of the triangle is a distance x from the origin to where the triangle is drawn. And then from the x-axis to the point on the terminal side, we have a distance y. And then we have this distance from the origin to the point on the terminal side that we're going to call r. And that's going to be really important later, but for now, we're just going to be like, it's r, okay? Well, knowing what we know about the six trig functions, we already know that sine is opposite over hypotenuse. So if we indicate where theta is, the opposite side is y and the hypotenuse is r. Well, that matches exactly what we had up here, really. We just, instead of calling it y, we called it b, and it was b over r. Well, it's the same thing. It's just y over r now. Cosine we know is the adjacent side over the hypotenuse. So this picture that we've drawn, that's x over r. Well, that's exactly what we had up here, except we were calling the point AB and we had a over r. Well, a represents the x coordinate. So let's just call it x over r. Tangent is in the original drawing, we had b over a, but for us, it's going to be y over x. And that should make sense because tangent is the opposite side over the adjacent side. Now, for cosecant, secant, and cotangent, let's use those reciprocal identities. So we know that cosecant is 1 over sine, which tells us it's just the reciprocal of sine. So cosecant is going to be y over, or excuse me, is going to be r over y. We know that secant is the reciprocal of cosine, so it's going to be r over x. And then cotangent is the reciprocal of tangent, so it's going to be x over y. Okay, so it's exactly what we did at the beginning of 7.4. We're just going to go ahead and acknowledge that the point on the terminal side lives in the Cartesian plane. It's a regular old xy ordered pair. Okay? Now, let's talk about similar triangles. This is kind of important because we're going to be building something called the unit circle. And essentially, it's created with loads and loads and loads of right triangles, essentially, okay? And so what we need to understand is that we could draw many, many circles with these right triangles that all have the same angles. And essentially, the ratio of their sides are going to be the same. That's kind of the heart and soul of what we're going to talk about here. So let's talk about similar triangles. So definition, it says two triangles are said to be similar if they have the same shape. That's important. They have to be the exact same shape. They're just different sizes. So one is a scalar multiple of the other. So that just means here that one is a scalar multiple of the other. Meaning, if we took the lengths of the sides of one triangle and multiplied them by the same whole number or the same natural number, we would get the lengths of the sides for the other triangle. Okay. Now, when you're dealing with similar triangles, when we say they're the same shape, what that technically means is that corresponding angles are congruent. Corresponding just means angles that are in the same location from one triangle to the next. So even though these triangles are different sizes, the angles are exactly the same, okay? And we'll prove this to ourselves in just a moment. And then corresponding sides are in proportion. So that means, again, since we know that one triangle is a scalar multiple of the other as far as the lengths of sides are concerned, there's going to be this proportional relationship between the lengths of the sides from one triangle to the next, okay? And what's really cool about this for us is this right here. The value of the trigonometric functions will be the same. So it doesn't matter which triangle you're looking at. If you're finding sine of a particular angle, you're going to get the exact same ratio from one triangle to the next. Okay? So let's think about what some of this is going to look like for us. Okay, so let's first talk about corresponding sides and corresponding angles. So let's say for the smaller triangle, side AB, well, it's in the same location as side DE. So those are corresponding sides. Let's switch colors. Let's say AC, whoops. AC is the hypotenuse, so it's going to match up with the hypotenuse on the second triangle, which is DF. And then finally, the base of the triangle BC is going to match the base of the second triangle, which we're going to call EF. Okay. Now the angles also are going to be, so like when we talk about corresponding angles, they're going to be in the same location from one triangle to the next. So the first one, it's pretty easy. We know we've got our right triangle. So this is our right triangle. So again, they're in the same spot. Okay. Now, as for the other angles, if we're in the upper, like the top angle, let's call it theta 1. And let's do that for both triangles, okay? Corresponding locations. So they're corresponding angles. It means they're in the same location from one triangle to the next. And then let's call the other bottom triangle, let's call its angle theta 2. Okay, that's going to be important in just a minute. We're going to answer a couple of questions about these triangles, and we need to know where the theta 1 and the theta 2s are. Now let's talk about the ratio of sides. So we know that AC corresponds to DE. And AC has a length of 8 and DE has a length of 24. So the ratio of sides is 1/3. So that tells me that the smaller triangle, the length of the sides are 1/3 of those of the larger triangle, or the larger triangle has lengths of sides that are 3 times those of the smaller triangle. Now, I do want to tell you right now, these triangles are not drawn to scale at all. So this is kind of, pretend they're drawn perfectly into scale, okay? So essentially what that means is if I took 8 and I multiplied it by 3, I would get 24, okay? Now we know that BC, that's the green, corresponds to EF, okay? And we know that BC equals 6. So if I were to take 6 and multiply it by 3, I would get 18, which has to be the length of EF. So this has to be 18. Now we're kind of stuck when it comes to AC and then DF. So what we can do is, knowing AC is a right triangle and we have the two legs of the triangle, we could just use the Pythagorean theorem to find the length of AC, and then we can use that, the fact that the bigger triangle, the length of the sides are 3 times larger than the smaller triangle, to figure out the side DF. That was kind of a mouthful, but bear with me. Okay, so down here it says find the remaining sides of both triangles. Well, we found EF, okay? So we can already say with a fair amount of confidence that EF is 18, okay? So that leaves us with AC and DF that we still have to find. Okay, so for AC, we can use the Pythagorean theorem. So to find AC, we're going to use the fact that C squared equals A squared plus B squared. Okay, that's just the regular old Pythagorean theorem. Let me shrink this just a bit so we can see better. Okay, so we don't know what C squared is. That's always the hypotenuse, but we do know that A is 6 squared and B is 8, so 8 squared. So let's see, we get C squared equals, well, 6 squared is 36, 8 squared is 64. I was about to say 46. I guess I had a moment. Okay, so let's see, 36 plus 64 is 100, so C squared is 100, and if I were to take the square root of both sides, I would get that C is equal to 10. So that tells me this length right here is 10. Well, if AC equals 10, we know that DF equals, hang tight, we know that DF is going to equal 3 times AC. So DF is going to be 3 times 10, or 30. Okay, and this is all true because we know that these two triangles are similar, mostly because I told you, but we're proving it right now. Okay, now for part B, it says find the value of sine of theta 1 and sine of theta 2. So what we're going to do is we're going to find sine of theta 1 for both triangles and sine of theta 2 for both triangles, so that we can prove to ourselves that if we're dealing with similar triangles, this right here is true. The trigonometric functions will be the same. Okay, so let's scoot. I need a little bit more space. Okay, so let's do big triangle and small triangle. I feel certain there's a more technical, formal way to say this, but we're just going to call the smaller triangle small and the larger triangle large. Okay? So on the smaller triangle, if I'm looking at sine of theta 1, make note of where theta 1 is. It's right here. Okay? And we know that when we're dealing with sine, it's the opposite side over the hypotenuse. So if I look at sine of theta 1 on the smaller triangle, I get the opposite side is 6, the hypotenuse is 10, so we would get that sine is 3/5. Okay, well, let's look at sine of theta 2, still on the smaller triangle. So sine of theta 2, we're down here now. Okay, so sine of theta 2, again, from theta 2, the side opposite has a length of 8, and the hypotenuse has a length of 10. So we get 8/10. Well, 8/10 simplifies to 4/5. So at this point, sine of theta 1, we're saying, hey, it's 3/5. Sine of theta 2, we're saying 4/5. Now let's compare that to the larger triangle. Now, if what we said about trigonometric functions on similar triangles being the same is true, we should get the exact same value. So let's see if we do. Okay, sine of theta 2 for the or let's do theta 1, sorry. Sine of theta 1 on the larger triangle. Well, we know theta 1 is up here. The side opposite this has a length of 18, and the hypotenuse has a length of 30. And if we were to simplify 18/30, 18 and 30 are both divisible by 6. So 18 divided by 6 is 3. 30 divided by 6 is 5. Well, look, we got the exact same value. So this is starting to become fact for us. We're proving it to ourselves that trigonometric functions, when applied to similar triangles, are going to be the same. So now let's go ahead and just verify with sine of theta 2. Well, sine of theta 2 is down here on the larger triangle. The side opposite that has a length of 24. The hypotenuse still has a length of 30. 24 and 30 are divisible by 6. So 24 divided by 6 is 4. 30 divided by 6 is 5. And again, we have proven that with similar triangles, the trigonometric functions are the same. Now, if you want to verify further, you can pause the video and find cosine, tangent, cosecant, secant, and cotangent of theta 1 and theta 2. You don't really need to. We've done enough here to prove it. If you want to, knock yourself out. Okay? So this should have all kind of been reviewed. We're just proving that if we have similar figures, trigonometric functions are the same. And then we reviewed this idea of drawing an angle in the Cartesian plane with a point on the terminal side and what the six trig functions would look like. Okay?